All right, thank you. So my name is Marc Newlin, and I'm giving a talk today about the processes that I use when I reverse engineer wireless protocols and devices. I'm on the security research team at Bastille Networks. That involves doing protocol decoders, reverse engineering unknown protocols and implementing software-defined radio decoders for them, as well as doing vulnerability research. I've taken kind of an unusual path to get into the security space, so I'll provide a little bit of background. Back in 2011, I competed in the DARPA Shredder Challenge, which was a competition to figure out how to reassemble shredded documents. And until that time, that was the most complicated, difficult project I'd worked on. But I discovered that I'm kind of a fiend for these really hard problems. So a couple years later, DARPA announced the Spectrum Challenge, which was a software-defined radio hacking competition. And I didn't know anything about SDR at the time, but I signed up after my positive experience with the Shredder Challenge. I ended up doing well on that, and through that competition, I found my way to Bastille, where I am now. And then about 9 months ago, I joined our vulnerability research team. Then my first project on that team doing threat research turned into Mousejack, which is a collection of keystroke injection vulnerabilities I found in non-Bluetooth wireless mice. And so the context at which I approach this is kind of coming in from a relative outsider to the security space and figuring out how most efficiently can I tackle these problems. So we're going to start with a bit of a primer on radio stuff. This is from my context as somebody without the fundamental education in that space. Then I'm going to discuss how we can use open source intelligence to increase the speed of the reverse engineering process. So that will be, what information can we get to take work away that we otherwise would have to do? And I'm going to walk through the process of reverse engineering the specific Radio Shack 2.4 gigahertz wireless mouse. And then finally, I'll do a demo of a Mousejack attack, which was the result of these methodologies. So let's talk about radios. So on a high level, we have hardware and software-defined radios. The hardware-defined radios, that would be your Wi-Fi dongles, your Bluetooth dongles, your wireless mouse dongle, the cellular modem in your phone, and it's going to be anything that's purpose-built to do one thing really, really well. But the problem with hardware-defined radio is you can't do a lot of research things with it because it does one thing really, really well. But if you don't know what that thing is that you need to do, it's not going to be very useful. So software-defined radio allows you to have a high degree of reconfigurability. So you might have a wide range of frequencies you can tune to, varying bandwidths. But the drawback is that it doesn't know how to do any one thing. So the SDR will just send this raw radio data to your computer or to an FPGA. And then you have to implement the functionality that makes it a Wi-Fi radio or a Bluetooth radio or whatever. But a very useful tool for doing this kind of reverse engineering because you can reconfigure it on the fly as you're figuring out what it is that you're looking at. So modulation is kind of a fundamental concept of how you modify a radio carrier wave to encode your data. So on this picture here, I can't see it very well, it's somewhat blurry, but this is a FSK modulated signal from the hotel room. And it goes left to indicate a bit 0, and it goes right to indicate a bit 1. And this is a very simple type of modulation, but it's very common in these low-power wireless devices because it's a low-complexity receiver to implement. And therefore, you don't need a lot of processing power, and you don't need a lot of battery to implement the receiver. Another common low-power protocol or modulation scheme is OOK, which is on-off keying. This is also very straightforward. When the transmitter is on, it's a bit 1. Transmitter is off, a bit 0. Also common in these low-power devices because it's low complexity. Then you have some other modulation schemes down there. You have QAM and OFDM, which are used in 802.11, as is DSSS. You have frequency hopping spread spectrum, which is used in Bluetooth. But the gist of this is that you don't need to really understand the fundamentals of how these modulation schemes work, because in GNU Radio, you can simply drag and drop blocks which have all that abstracted away. And as long as you know what modulation scheme you need, you can turn the radio waves into bits. So then there's the concept of symbols and samples and sampling. So a symbol is one duration in time that represents one or more bits. So for frequency shift keying and on-off keying, each symbol is one bit because you're either on or you're off, or you're over here to the right or to the left in frequency. But with the higher order modulations, you can have 2, 3, 4, 5 bits per symbol. But typically, these low-power devices have modulation schemes with 1 bit per symbol because, again, it requires a Bohr quality receiver and easier to implement. Another thing to remember is that you need to sample at twice your symbol rate. So if you have a frequency shift keying modulated signal, each bit is going to be one symbol. And because of math, which I don't understand, you need to sample it twice that. So if you have a 1 megabit per second frequency shift keying signal, you need to sample at 2 megasamples per second. And just knowing that you need to sample at 2 samples per symbol is sufficient to use GNU Radio to demodulate this data. So then we have frequencies and frequency hopping. Frequency in this context is just a specific channel that a device operates on. A device might use one or more channels. It might hop between these channels. Bluetooth, for example, will have deterministic frequency hopping between 79 channels. You'll have something called frequency agility, where a transceiver will select the channel that has the least interference. But a lot of devices will just camp on one channel and stay there. Then you have channel coding. This is adding redundancy to the data you transmit. And this can be either adding additional bits, adding parity bits. You have ARQ, where the receiver, if it gets a packet out of order, it will ask the transmitter to send it again. And these are just mechanisms to make sure that the data gets across. One thing to note from a reverse engineering standpoint with channel coding is that if you're using a convolutional code, for example, the bits transmitted over the air will not look like the bits that you're actually transmitting, not look like the original payload. And so if you're looking for the original payload in this demodulated data, you may not see what you're expecting if channel coding is used. So now we'll talk about the process that I go through to reverse engineer a protocol. And we have, so this is where everything started. So with Mousejack, I was looking at a large number of devices in a relatively short period of time. And so it was approximately 50 keyboards and mice, 4 different families of transceivers, and around 20 different protocols and payload format behaviors. Because it was such a wide range of types of devices, it necessitated being very efficient about going through the process in order to not waste time. And so as a result of going through all these devices, I've developed a fairly efficient way to do this. So there are a number of things that we're trying to get at when we reverse engineer a device. I like to think that there's both the business and personal case. So from the business case, we want to see, can we uniquely identify this device? What type of device is it? Is it exhibiting normal behavior or aberrant behavior? If there's an attack happening, can we recognize that? But then for the personal case, it's just very satisfying to be able to reverse engineer these things. And it's when you crack it and you understand how everything comes together, it's great. And so there's kind of that combination of personal and business motivations that go into this. So then we have kind of 3 cases of devices that we want to reverse engineer. The top, fully standardized, that's not really doing any reverse engineering because everything is defined. So the physical layer, so the modulation, the frequencies, the channel hopping, all of that exists in a spec that you can go read. Not to say that certain devices will not implement it correctly, but the idea there is that everything you need to know is available for you already. Then we have partially proprietary. This would be cases where you have maybe a transceiver, which is documented. So you might know what the physical layer is, so the channels and modulation, but you may not know what payloads are being transmitted. And then you have fully proprietary devices where you know nothing about it. So you don't know what transceiver it uses, you don't know what protocol it uses, and you have to figure all of that out. In the case with this Radio Shack mouse, it's fully proprietary in that there was no information available, no documented information available about this to start with. So with this mouse, we really need to do some open source intelligence gathering and find out what information is available there to speed up the process, because if we're starting blind, it's a pain in the ass. So we have 5 stages here. So we're going to start by doing open source intelligence. This is going to be using the internet to find out what we can about this device and how it operates. We're then going to verify with the spectrum analyzer that the information we got on the open source intelligence is correct. So this is going to be visually looking at it and saying, hey, does everything line up? Make sure we're on the right track so we don't waste more time. Then ARFs to bytes. I want to point out ARF is what we internally call radio waves, or it's kind of a universal word. But in this context, ARFs to bytes means taking the radio waves emitted by this device, in this case, mouse click or movement data, and turning it into bytes on disk that we can then parse and operate on. Once we have those bytes on disk, we then need to figure out what the format is of the packets that were sent over the air. And then we need to figure out what payloads are in those packets and what is the protocol and behavior of the device. So first we'll look at the open source intelligence process. There are a few good resources for this. The FCC in the United States has a wealth of information. There are also product specifications you can get for certain transceivers. So you might have a case where a device uses a transceiver. How they use it is proprietary, but the underlying physical layer communication of the transceiver is documented. And so in that case, it's useful to find that spec sheet, figure out what configurations they might be using, and you can save time then by narrowing down what you're looking for. And then the Google is fantastic. Enough said. So if everything goes perfectly, we really can learn all the information we need to know about how this device operates. So that might be all the physical layer properties. It also might be the packet formats and protocol behavior, depending on the device. But at the bare minimum, we're hoping to find at least what frequencies does it operate, what modulation does it use, and what channel widths does it use, so we can turn those radio waves into bytes. So in order to sell a device in the US, you have to go through the FCC certification process. So it starts when you make your device. You then send it off to an accredited test lab. The test lab will operate your device in an environment, and it will basically see what the RF behavior is. So that might be things like what channels does it run on, what's the duty cycle, what power does it transmit. And then the test lab generates a test report. That then gets sent to a telecommunication certification body, which says, did this test lab do everything correctly? Did they follow the procedures, and so forth? That then gets sent to the FCC if everything passes. They get an FCC ID, and all these documents get posted online. The FCC website makes these available, and then we can use those as a great source of information. One thing to note is that many devices will have one certification for all of the regulatory bodies. So we'll have an FCC ID, an IC ID, a MSIP ID, and so forth. And so for devices sold outside of the US, you can usually use the FCC if it's gone through the same test procedure. So FCC exhibits are what they call the documents that are posted when a device is certified. You have a number of different types of documents, and you can get them by looking at the FCC ID on the device, plugging it in at that URL, and then get a list like this, usually a bunch of PDF documents. So there are a handful of exhibit types that are relevant to the reverse engineering process. Test reports are the absolute best. This is where the RF emissions are evaluated. Part of the difficulty is that you have a wide variety of formats of test reports. So you have 2,500 test labs. Each one has different report formats and varying degrees of information. And there's no guarantee that any test report will have any specific information that you want, but it's usually a pretty useful source. Internal photos is fantastic. They open up the device, take photos of it, so you can look there and look for specific model numbers on the RFICs and that sort of thing. User manuals are interesting because you have a lot of them are consumer-facing, nothing terribly useful, but some of them will have deep technical information for whatever reason. Schematics, usually these are kept confidential. So when you submit a device to the FCC, you can request that certain exhibits be kept confidential either temporarily or indefinitely. Some labs and TCBs will, for whatever reason, leave their schematics open. In that case, you can often get RFIC information and so forth. And then operational descriptions, again, usually confidential, but usually has some good, deep technical information. So with the test reports, this is looking at, the FCC has certain regulations for how a device can operate. So this is evaluating for transmit power, bandwidth, frequencies, and duty cycle. But it often contains modulation types, frequency output information, and it's hit or miss, and it varies between the labs. So this is an example of a test report from Bureau Veritas. They're probably the largest test lab, and they're nice because they have a good amount of structured data. So in this case, this is from a Logitech mouse, and we can see here that it uses GFSK modulation. It operates in this frequency range, tells us how many channels. Elsewhere in the report, it tells us the specific channels that it operates at. This is kind of the best case scenario for what you can get from a test report. Unfortunately, most will have less information than this. And it also gives us there the transfer rate, so we know that it's a 2 megabit data rate. This is from the test report from this Radio Shack mouse. Here it's clearly not as structured of data, but we can see, here we see 76 channels, 1 megahertz channel spacing. We don't yet know what the modulation scheme is. This is from the Intertech test lab. And now the dongle, in this case, was certified separately by Neutron Engineering. In this case, it's probably some other OEM made the product and whatnot. But in this case, we have more structured data. Unfortunately, this is different information than we saw from the mouse. So here we see 34 channels versus the 67 from the mouse. But we see that it's GFSK modulation. We can see the data rate of 1 megabit. And it's, these discrepancies between test lab reports for the same products can be kind of frustrating, but you just have to kind of filter through that and get a consensus for the available data. So with internal photos, this is kind of a frustrating thing. Some labs will have high resolution photos embedded in the PDFs, but a lot of them will have cropped or low resolution photos. Sometimes they'll take a permanent marker and just draw over the markings on the RFIC to make it difficult to find out what's in there. So it's hit or miss, but sometimes you can get useful information. So this is the internal photo of a Microsoft dongle. In this case, you can't make it out there in the image on the projector, but it has the markings where you can see what specific transceiver it has. This is kind of the best case where you can make out the transceiver, and it's something that's well documented where you can just go and get the spec sheet and then implement exactly what the spec sheet defines. This is the internal photo from this mouse. Unfortunately, there's no useful information. The RFIC is under a little epoxy mound there, and so really we can't gain anything from this. This is the internal photo from the dongle. Again, no useful data. And this is typical, but sometimes you can actually get out the RFIC model information from that. So schematics, this is really hit or miss. Most vendors will not make these available, but in some cases they are. And so in this case, for the Radio Shack mouse, we can actually see the specific model of the RFIC. Unfortunately, in this case, it's kind of a lesser-known manufacturer called Mozart Semiconductor who makes this. They don't have any publicly available documentation, but it's still something we can Google for later. And most of the big name companies will not make this data available. So operational descriptions and user manuals, again, really hit or miss. So the operational descriptions will say, this is on a high level how this device operates. Sometimes it will include transceiver information, physical layer operating characteristics, but as far as I can tell, there isn't any good structure for what this data has to be. And user manual, same thing. I mean, oftentimes it's customer facing, how do you use this? Oftentimes it has good technical depth. So this is the operational description from the Radio Shack mouse. Now here we have some weird data. So it says on there 2.4 gigahertz Bluetooth module. It's likely not Bluetooth, doesn't mention that anywhere else. Again, a case where you have this wildly varying data between the different available sources. But it does say that it's FSK, which lines up with what we saw elsewhere. It does tell us we have 67 channels, which lines up with what we saw in the test report for the mouse. And it also mentions the same MA4302 RFIC. Unfortunately, no more detail on the RFIC, but it lines up with what we've seen in the schematic. So this is from the dongle user manual. This is kind of an interesting case where you have physical layer information in the user manual. So this tells us, again, GFSK RFIC, 1 megabit data rate. We see this channel range. Apparently, you can only use it in a human house. It's unclear what that is intended to mean. And so now I Googled around a bit for this RFIC. Googling for the RFIC itself yielded nothing useful, but searching for mouse plus MA4302 produced this product, which is this company Sweeks. Appears to be a mouse with the same transceiver in it. So here we can get a little bit more data. We can confirm that it's FSK modulation. In this case, it says it's frequency hopping. We don't really know if that's the case or not, but it's additional information that we can use to confirm what we've received from other sources. Oftentimes, in these type of devices, you'll have a purpose-built RFIC. So this one seems to be made for mice. And so searching around for that, you might get some additional information. So now that we've gone through these sources, we have a fairly good idea of what the physical layer radio characteristics are for this device. So here we can say with confidence that is GFSK modulation. We can say with confidence that is this frequency range. We know that it has some number of channels that we'll still need to figure out. We know that it's a 1 megabit data rate. And it has said Bluetooth and frequency hopping, but that's likely not the case, but we'll confirm that. So now that we have this information, we can have the device generate some traffic, in this case, moving it around or clicking the mouse button or whatever, and look at that with a spectrum analyzer using a software-defined radio. And with this, we can confirm whether or not the information that we have so far is accurate. So there are a number of tools that are useful for this kind of scenario. You generally want a software-defined radio. That's hard to do without. An RF test enclosure or Faraday cage is very, very nice for multiple reasons. You can get rid of any noise in the environment, and if you're fuzzing and whatnot, you can keep that contained. GNU Radio is a great software suite for abstracting away all of the signal processing and radio side of this. And so that allows you to not have any deep background in this, but still be productive. And then GR Phosphor is a spectrum visualization tool that you use with GNU Radio. Baudline is another spectrum visualization tool with GNU Radio. And then you need the device you're going to look at. So for software-defined radios, I like to use the USRP B210s, is what we have at work. They're a great device. There are a lot of different options for SDRs that are fairly cost-effective. You can get, depending on what you're looking at, you can even get away with these little RTL SDR dongles that are really cheap. They don't work in the 2.4 gigahertz range, but very accessible for a lot of projects. And again, with the SDR, we can configure it to be whatever physical layer we want. So in this case, we can tune it to the specific frequencies that the mouse is likely to use and define using GNU Radio how we're going to demodulate the data. So GNU Radio is a combination of C, C++ libraries as well as Python code. And it has modules or blocks, they call them, for demodulating all of the different modulation types, doing error correction, timing recovery. There are GNU Radio stacks for doing Bluetooth and Wi-Fi and 802.15.4 and all sorts of things. Really a great ecosystem around there. And the really nice thing is that you can mock up a prototype very, very fast without much forethought. So this is GNU Radio Companion. This is the user interface that sits on top of GNU Radio. And this allows you to drag and drop these blocks, which do different things. And so you can have a block which does your FSK demodulation, a block which connects to your software-defined radio, and so forth. And so it allows you to not really have to understand what's going on under the hood, but you can still get done exactly what you need to get done. So this is a screenshot of GR Phosphor. This is the spectrum visualization tool. So here we're looking at frequency on the x-axis and time on the y-axis. And so this is a snapshot of some LTE traffic. This is nice because you can tune your radio to a certain frequency and very quickly determine exactly what's happening. So you can say, hey, is there something there? Is there not? It's kind of good for doing these sanity checks. This is Baudline. So Baudline is an independent tool. And then there's the GR-BAZ GNU Radio block, or module rather, which allows you to wire up GNU Radio to Baudline. Baudline is nice because you can pause the spectrum as it's going down in real time and expand it. So this is a case of some FSK modulated data, and you can even see that it's going left for bit 0, right for bit 1, and you can almost visually make out what data is actually being transmitted. This is an example RF test enclosure. This is what we use at work. These things are really, really fantastic because you can put your devices in there, SMA cable out to your software-defined radio, USB out to your computer, and so you can interact with your SDR and your device the same way as you would out in the open, but you're protected from everything in the environment. For determining exactly what a device is doing, this is very valuable because you can know for certain that you're not looking at traffic coming from something else in the world. And so this is a very, very simple flow graph, which has our input from the software-defined radio there. Then I have an output to GR phosphor. And this is all you need to get up a spectrum visualization tool and visually verify that that information we got from the FCC documentation appears to be accurate. So in this case, we're camped at 2420 megahertz, looking at 40 megahertz bandwidth, because we think that there are 34 or 67 channels, but we don't know, is it hopping or not? Where does it lie in the spectrum? We want to look at as much as we can so we can quickly see what's going on. This is the setup inside the test enclosure. On the left, that USB goes out to the computer. On the right, that antenna connects out to a software-defined radio. And then it has gloves, conveniently, so you can operate the device and interact with it just like you would on the desk. So this is the GR phosphor plot from just the dongle alone in the Faraday cage. And the idea is that the dongle is going to transmit to the mouse, either AX or sync packets or whatever. And the mouse is also going to transmit to the dongle. So in order to be able to determine what is coming from the dongle, we first start with that. And we can see that it's transmitting these packets at regular intervals, and that it's camped at 2414 megahertz. Because it's transmitting at regular intervals, we can infer that it might be timing synchronization information. The way a lot of these devices work, the dongle will decide what channel it's going to be on. It will transmit this data. Then the mouse will search around, find where the dongle is, and then camp there. So it looks like that's what's happening here. So now we have the mouse and the dongle in the cage. That zoomed in view over there, this is a 3-packet grouping when I'm moving the mouse around. So the assumption is that the first packet is that dongle sync packet. The second packet is likely the mouse data. And then it's reasonable to assume that the third packet is the dongle acting back to the mouse. So even though we're just looking at this visually, we can start to make some assumptions about what the protocol behavior is for these devices. So now we can say with some confidence that we know, the modulation, we know that it's camped at 2414 megahertz. So now we can record some data and turn that into bytes using GNU Radio. So this is another simple flow graph. We're using a 2 megahertz sample rate because we're a 1 megabit data rate and we need 2 samples per symbol. So we're starting with the USRP input. We're demodulating the data. The output of the demodulator is 1 bit per byte, so either a 1 or 0 8-bit unsigned integer. So we're packing that into bytes so that we have 8 bits per byte. And then we're writing that to a file. So we can run this. It will capture the RF data coming out of the mouse and the dongle. And the result is that we have bytes in a file on disk that ideally represent what this device has transmitted. And so again, we want repeated sequences of packets. So if we're looking for something, it's easier to find something if it happens over and over and over again. So with the dongle by itself, it's sending these synchronization packets, and so we can just put it in there and hit go. For the mouse, in this case, I put my hand in the glove and just sat there and clicked the left button over and over again so we could have the same packet repeating in the output results. So now that we have these bytes on disk, we need to investigate them and try and figure out what packet format is being transmitted. Because we know, we can infer anyway that the bytes we have, some of them at least, have come from the mouse and dongle, but we have no idea what the format is. So we need to use common tools to get that data. So there are a number of components of a typical RF packet. You'll have a preamble at the start. This is used for clock synchronization and timing synchronization. So you have an oscillator in the dongle, oscillator in the mouse. They're not going to be synchronized because they're low quality. And so the receiver needs something to log onto. So you'll have an alternating sequence of ones and zeros, for example, and then the receiver can look at that, time its clock to match the transmitter, and makes it easier to correctly decode the data. You'll then often have a sync field or start a frame delimiter. This just says, hey, the packet is starting here. Sometimes a sync field is the address. Sometimes you'll have a sync field which is static for a type of device, and then you'll have an address after that. You might have a header which indicates what type of frame it is, what the frame length is, and so forth. Then you'll have the payload, so the actual data being transmitted. That might be just the raw payload, or it might be the payload that has been encoded with some channel coding and redundancy. That's hit or miss if you don't know what the protocol is. You'll frequently have a checksum at the end, so you can know if the correct data was received. And then you also might have a postamble. With the postamble, this is for additional time and frequency correction. So you can compare the preamble to the postamble, see what changed, and further clock state of the transmitter. So I'm a big fan of using these just regular Linux command line tools because you can just really quickly get to the data. So I start by using XXD to turn the byte output from GNU Radio into a long hex string. And then we can grep that and do these normal things like we would on a text file. And it really makes it easy to operate. Now, one problem is we're operating at these byte boundaries. So we've taken these bit outputs and we've packed it into bytes. But the start of a packet might fall at one of these bit offsets. So it might start 3 bits into a byte. Because of that, we're not going to see every single packet. But the assumption is that at least some of the packets will fall at a byte boundary, and then we can decode it. So a preamble is often going to be a tone, which would show up as 00 or FF hex bytes. It also might be alternating ones and zeros, which shows up as AA or 55 hex characters. And so we start by simply grepping for repeated sequences of those characters and seeing what shows up in a repeated manner. And in this case, we have that 4F followed by 12 A's, which shows up, so the longest repeated sequence that shows up quite a few times. And so we can make an assumption that that is likely going to be the preamble that the dongle is sending out with its sync packets. We don't know that for sure, but it's probably a safe assumption. So now we want to find what sequence of bytes follows this preamble. And so we can just use grep again, and we start with the preamble. In this case, we're looking for 4 Fs followed by either 12 As or 12 5s. Because if you have FFFF and 12 As and you shift it by 1 bit, you get 4 Fs followed by 12 5s, and so we want to cover all bases. And then we want to look for the longest sequence which follows this preamble. So in the grep string up there, there's a 16 at the end, and that is the number of characters following this preamble. That's not a given number, and so in this case, I started with 1 and worked my way up until at 17 characters, there was no longer repeated sequences. So you can assume that that 16 is probably the full length of the packet. And now these were the dongle sync packets. So we want to do a sanity check and make sure that it looks like they're following the behavior we saw on the spectrogram. So in this case, we use grep again. And we have the B flag passed into grep to give us the offset in the file where these packets occur. In this case, we can see that they show up in multiples of 2000 offset, more or less. So we have kind of even spacing, and so this is probably a safe assumption that these are the sync packets that we saw on the spectrum analyzer. So now we can start looking at the capture of the mouse plus dongle in the Faraday cage. Now, because we've made this assumption that this byte sequence is a packet transmitted by the dongle, we can just use sed and remove that from the output of the mouse plus dongle. The idea there being that if we have whatever's left over was transmitted by the mouse and probably not the dongle. So we run sed, isolate the mouse packets, and then we go through the same procedure looking for the preamble for the mouse packet. In this case, we have a potentially different preamble. We don't have the same 4s followed by 12 a's or 5s, and it's not immediately clear which one of these might be the preamble. So we go through the same process of looking for repeated sequences following these, and just go down the list and try each one of them. Takes a bit of time, but necessary in this point. So in this case, what worked the best was 4 a's followed by a number of bytes. And however, we don't have just one packet that shows up repeated a bunch of times. We have this list here. And we see we have the one character which varies. So this is likely going to be a sequence number. Everything else is the same in the packet up to that point. We have that varying there. And then we have these 2 bytes at the end which vary. So that tells us that it's possible that this is a sequence number, that when that changes, that we're modifying a checksum at the end. So that we can infer then that we're probably going to look for a 16-bit CRC at the end of the packet. And now we can do the same sanity check. The ellipsis in the grep there is just the grep string for all of the packets that we think we found from the mouse. In this case, we see more or less similar even spacing. They're spaced out further apart because I was manually clicking the mouse to generate this instead of doing the automated process from the dongle. But it looks like it lines up, and so we've probably found packets coming from the mouse. So now we have these candidates for what we think are the packets. We have the dongle sync packet up there. That's the only thing we've seen transmitted by the dongle that we're aware of. We then have this list of mouse packets. And we have those 4 bytes, which are the same between the dongle and the mouse packet. Because we have that same in both cases, the assumption is that that is going to be either a sync word shared by the devices and or the address. And then we have these preambles and postambles. Both the dongle and mouse packets end with FF. And then we have the 4A preamble for the mouse packets, and then that 4S followed by 12A's preamble for the dongle. And now the question is, what is this 16-bit CRC? Is it a CRC? Could it be something else? What is it? So the lowest hanging fruit is this tool called CRC revenge. And you can just pass that a sequence of bytes, hex bytes in this case, and it will run through common and then brute force uncommon CRCs to tell you, is the same CRC at the end of each one of these byte sequences. In this case, as they were, no dice. It didn't find anything, and that's frustrating, but that happens. So now one thing to consider is a lot of packets will be whitened, and this works by XORing the payload of the packet or the entire packet with some value, to avoid long runs of 1s and 0s in the data and so forth. There's no magic bullet here. I just went through and tried XORing a lot of common whitening sequences. So in this case, XORing the entire packet with 0x5a bytes was a magic bullet. But then the last 2 bytes in the packet, the checksum, were in reverse byte order. So in this case, XORing the entire thing with 0x5a repeated, and reversing the last 2 bytes for the checksum worked. And then we pass it into CRC revenge. And then we see that it is the X modem variant of CRC16 CCITT. And now we know, OK, we have the full packet format, more or less, for the mouse. So we know it has this preamble. We're assuming those 4 bytes are the address. It may or may not be because we only looked at one mouse, so we can't say for certain that another mouse would have the same or a different address value. We know that it has a payload of 3 bytes, followed by the CRC and the postamble. So now that we've figured out the one of the packet formats, then we can go back and start to figure out what is a protocol behavior here. And so this requires usually some additional time and testing in devices. So the low-hanging fruit here is just getting another one of the same mouse, and you run through the same procedure and see what changes. In this case, the second mouse and dongle had a different 4-byte value for that sync word or address. So now we can assume that those 4 bytes are in fact a unique identifier for the mouse and dongle and are specific to each device pair. You want to go back and look at other packet formats as well. So this was just looking at mouse click, so you want to go back and generate the same data by clicking the other button or doing the scroll or moving the mouse slightly left and slightly right and so forth, and just work your way through and build out all of the different packet formats. But then we have these potential acts, and it was unclear initially what those were, but it looked like they were acts. We haven't seen those in the decoded data yet. But what we can do is simply grep for the address we have. Now that we know that that's the address, grep for that in the data outputted by the dongle and the mouse in the Faraday cage. And we can see that we have that 4-byte payload sequence following the mouse packet by 300 microseconds. And so the assumption is that this is, in fact, the ACK. With only 4 bytes, we, of course, don't have room for CRC. But going back and testing this with different types of mouse movement packets and clicks and whatnot, and it quickly became apparent in this case that that was the ACK, just not protected by a CRC. So we have an idea of what the packet format is for both the mouse and the dongle. And now we want to verify what the timing is. So the assumption here, based on the spectrogram, is that we have the dongle transmitting packets every 16 milliseconds. Just following every dongle packet, the mouse has an opportunity to transmit a packet. If it does, the dongle then acts a few hundred microseconds later. And so knowing this behavior, we can then potentially build a fuzzer, start transmitting, etc. So we have knowledge of the packet format, but we don't know what data is transmitted in the payloads. This can vary wildly, but in this case, we know what we're expecting to happen. So we know, we can generate the same thing over and over again for clicking and movement and so forth. And so we need to simply collect a bunch of data, see what changes in the payload when we change different behavior, so different clicks or scrolls or whatever. And then based on that, we can infer what the format is of the payloads being transmitted. And so in this case, we have a sequence number, which is 1 nibble. We have a 1 nibble frame type, which changes between movement versus scroll and click. Scroll and click have a button state, so that's going to be down or up. We have a button type, which is either scroll wheel or a regular button you can click. Then we have the button delimiter, so left, right, scroll, up, down, etc. And getting this data is just a matter of going through the motion of literally moving the mouse and seeing what changes. So now we have a fairly good model of both the packet and payload formats and protocol of this particular mouse. So we know we have 4 packet formats. We know we have the dongle sync packets. We have the ACKs. We have movement, click, and scroll packets. We know it's GFSK modulated at a 1 megabit data rate. We know that it camps on 1 channel. In this case, the other mouse camped at, I think, 2420 megahertz and never changes. So it appears that for the lifetime of the devices, that they're likely at the same channel. We know the TDMA information. We know the dongle transmits the sync packets, and so forth. We know that the mouse will always follow the dongle sync packets. This is not always the case, but in this kind of TDMA setup, you'll usually have the mouse will get its timing information from the dongle. And we're inferring that it uses 34 channels. The channels that we saw in use were at 4 megahertz offsets. So based on that, it's likely the 34 channels that we saw in the docs and not 67. It's not Bluetooth, it's not frequency hopping, and we know that it uses the X-modem variant of CRC CCITT. Now, this process for the mouse was one way of doing things. But then I've also been looking at, in my hotel room in the past couple days, this little tiny quadcopter. And for this, I didn't have the Faraday cage here, just the SDR on my laptop. And so I was visually looking at the data using baudline. Now, here's what it looks like when you have just this remote turned on. You can see with the remote on that it's transmitting some kind of same synchronization burst or whatnot to the quadcopter every 15 milliseconds. And we can see that something's happening there. Now if we zoom in a bit, this is with the quadcopter on and communicating back to the controller. We have those top bursts in each set, which line up with what we saw with the controller alone, and then the second, more powerful burst below. So that might be ACKs coming back from the quadcopter. And the point of this is that you can do a quick visual analysis and get some useful data without even having to break out the Faraday cage and do anything too complex. And here we have zoomed in further on the packet for the controller, the packet from the quadcopter, here, because we can actually see the frequency change from down to up for 0 and 1, you could actually work out exactly what's being transmitted by simply visually looking at it and writing down what each bit position is. This is a little bit less robust of a mechanism, but for quick and dirty analysis of protocols, this kind of thing works pretty well. So to recap the process used here, we start, do our open source intelligence, we look at the FCC documentation, we Google around and so forth, and we find out everything we possibly can about the physical layer operating characteristics of the device. We then verify it with the spectrum analyzer in the Faraday cage if possible, and make sure that that information looks correct. We then use computer radio to turn that into bytes or bits on disk that we can just grep around and start finding these packet formats. Once we have the packet formats, then we can work out the protocol format, or protocol behavior, and the payload formats for the device. And this process is pretty effective, and for something like this, it's a few hours in an afternoon to get a full model of how it works. And then once you have that data, then you can apply it to building a fuzzer or whatever your next research steps are. So now I'm going to do a demo of kind of what the result is of all this research. So Mousetrack is a bunch of keystroke injection vulnerabilities I found in different types of non-Bluetooth wireless mice. For doing this kind of injection demo, I like to use these hardware-defined radio dongles. So in this case, this is a dongle from the Crazy Fly, which is an open source drone project. It's the same transceiver as Logitech uses in their wireless mice, but it also has a power amplifier and low noise amplifier. And this is nice because once you know exactly how a device operates, you can use something like this, and it does one thing very, very well. It's small, compact, effective, etc. With this, we were able to actually do keystroke injection from 225 meters away using one of these and a directional antenna. So it's a neat little device. And so in the case of the Logitech attack, there are 3 vulnerabilities being exploited. There's a forced pairing vulnerability. So the normal behavior is you put the dongle into pairing mode with host software, and then it stays in pairing mode for 30 to 60 seconds, and then you can pair new devices during that time. It turns out it's possible to also force pair a device at any time. So as long as you know the RF address of a mouse or keyboard that is paired to it, you can pair your own device, which turned out to be a problem. Another neat thing, you need to pair a keyboard with a dongle in order to inject keystrokes, but you can actually structure the pairing sequence in such a way where you pair a device which is a keyboard effectively, but shows up to the end user as a mouse. And still having a new device paired, not good, people will notice. But if it looks like a mouse, maybe it's less suspicious. And then the really fun thing is this unencrypted keystroke injection. So Logitech encrypts the communication going between keyboards and the dongle using 128-bit AES, but they don't verify that incoming keyboard packets are encrypted. So the vulnerability is simply a matter of sending the unencrypted equivalent of what the keyboard sends, and the dongle gladly accepts it and will allow you to inject keystrokes that way. Logitech has issued a firmware patch for this dongle. If you use Logitech devices and you haven't patched, please do. It's important. So I'm going to plug a Logitech dongle into my laptop down here. And then on my other laptop, I will plug in this crazy radio dongle, which will allow me to send the commands to execute the attack. Just give me 1 second to get this set up here. And so in this case, this is just a Logitech M510 mouse with the standard Logitech Unifying USB dongle. And there are, one thing to note, there are 2 different variants of these Logitech Unifying dongles. They have one with Nordic Semiconductor transceivers and another version with TI, Texas Instruments transceivers. Both versions are vulnerable and both need to be patched. So I'm going to open up the Logitech Unifying software here so we can see that we're actually pairing a new device. Okay, so here we have this one mouse which is paired with a dongle, and that's the expected behavior. And now I'm going to run a script on my laptop here, the other one. And this is going to issue commands to pair a new device with the dongle. The dongle is not in pairing mode, but in this case, it doesn't matter. Okay, so we run that, and then we'll see our new device show up. In this case, I've named it mousetrack to make it visually distinct, but you can arbitrarily set what it's titled. You can also arbitrarily set what device type it is. So you could have it show up as a mouse or a keyboard or trackpad or whatever. So now I'm going to, so the output of my script here is the wireless address of the newly paired device. So each device paired with the dongle has a distinct address. So I'm going to feed that into another script, which will execute a keystroke injection attack. This will bring up a notepad and just type a little bit of text. And I'm next to this laptop now, but we've shown with range testing that you can do the exact same thing with the exact same reliability at 225 meters away. And that range applies across the range of vulnerable devices that we've tested. It's definitely concerned that you should patch your devices. The other vendors outside of outside of Logitech don't have the ability to update the firmware on those devices. So if you're using a non-Bluetooth wireless mouse and it's not Logitech or Logitech and unpatched, I would definitely change your behavior. Anyway, that's what I've got. Any questions? Thank you.
I have a question.
Yep.
How did you come up with those whitening sequences that you tried?
I guessed. Yeah, that was it. Thank you.